In Lab 3, you'll be creating a class for your blue motor that you'll use for your project. You'll use that motor to control the 4-bar. And so in this lab, you'll write the class and run a bunch of tests on the motor using both a DC power supply and using the battery supply from your ROMI with a PWM signal. Um, so here's a picture of the setup. And these two parts, you can, if you're remote, you can 3D print them. If you're not remote, you can still 3D print them if you want, so that you have your own copies. Or they'll be these parts will be available in the lab. Let's see if I go to. So here's the STLs. The drum you'd want to print with support turned on, and there's the winch support. So you have the both SolidWorks models and the STLs if you want to print them. But as I said, if you're on campus, there will be sets available in FOISE 103. So let's just look a little more at the things that you'll be doing. You'll want to set up the push button, and there are slides that explain how to do this. Right, if you go to this lecture module and open up this right here and go pretty much to the end. So you're going to be this is a sample using button A. You'll want to use button B because buttons B and C now are being used for other things. But so you have a push button on your ROMI, button B, and you can set up code like this. You can see what this does. Whenever that button is pushed, it sets the time to 100 milliseconds past the current time, and then it just sits in this while loop until that time is over, and then it prints you want it to print the counts at that point, and then you just keep the button down, and so that every 100 milliseconds it will print the count. Okay, so you'll run these tests with a DC power supply. So you'll need to get 11 screenshots of showing the time in milliseconds, the count, and then the angular velocity in RPM. So in other words, if every 100 milliseconds you get the count, the encoder count, and you know how many counts there are per revolution, and you know the time period was 100 milliseconds, then you'll be able to calculate the RPM at every 100 milliseconds. For the 4.5 volt DC load supply, you'll get the RPM with no load, and then you'll hang around 40 grams off that drum and around 80 grams, and then repeat the same thing at 6.75 volts and 9 volts, except at 9 volts you'll also do in 6.75 volts you'll also do 120 grams, and there's 120 grams at 9 volts as well. Okay, and then so for this test, you use the ROMI to read the encoders, but not to power the motor. The motor is being powered by the DC power supply. Okay, whereas in this test, it's being supplied by the battery power from the ROMI. And instead of doing 4.5, 6.75, and 9, that would correspond to, we want to look at a 50% duty cycle, right? Because you have 9 volts in the 9 volt available at the batteries. So a 50% duty cycle, you want to see if that mimics the 4.5 volt. 75% should be, you want to see how that compares to just a steady 6.75 volts, and then of course 100%. So you'll end up with you'll end up with 11 screenshots for each of these 11 tests right here. And let me just show you what that might look like. So that might look like something like this, right? Where you have the time, this is the time in milliseconds, and you can see that it prints out every 100 milliseconds here. So this is the time in millisecond. These are the counts, and then you can you write the program to calculate the RPM. okay? And it doesn't matter whether you're going forward or backwards. Obviously, we got minus signs here, but um, you want to get the magnitude of the speed. That's what we want. Um, okay, so you'll have screenshots like that, and then also for the PWM signal, you'll have 3 different screenshots where you'll grab use the oscilloscope, and you'll get something that looks like this. Set up the oscilloscope, so you can set the oscilloscope so it gives you the duty cycle. In other words, this is measuring the duty cycle, and it's going from 0 volts and shows the maximum. It's got a little spike there, 9.8 volts. So you'll have 3 screenshots like that. Okay, one thing I forgot to mention, when you do the DC power supply test, you can also read it will show you the current. So in other words, you want to set the maximum allowable current, up to something, I don't know, maybe like 1 amp or something. It's not going to draw that much. But when you run the test, you can, it takes a little coordination with a couple of people here to push the button on the ROMI to collect the encoder data, and then push the on switch on the DC power supply to run it at a particular voltage. But you'll also be able to read off the current that's being supplied to the motor through the DC power supply. Okay, so now once you've collected that data, you can put it. There's a template that's provided, and let's take a look at that for a minute. Right, so just as an example, I left in so this was some data that I collected. Obviously, you're going to use different data than this. You're going to collect your own data. So, I just put some weights in the cup that we hang off the drum, and got it till it was about 40 grams, about 80 grams, about 120, and then ran the test with the 9-volt DC power supply. And obviously you can calculate the torque. If you know the mass and you know the radius of the drum, you can figure out how much torque is being applied if it runs at a steady velocity there. And ran the test also with 100% duty cycle. And I didn't put the answers in here for you, but you can put your current values in here. And then this is again just as an example. It talks about plotting. You want to make sure you have clear notation here, axes, legends, right? The 9-volt DC, the 9-volt PWM signal. And you can put in the trend lines. These are just the linear regression equations, right? And change the variable names to make sure that it makes sense. And then, of course, you're also asked to find the stall torque, the theoretical stall torque. If you have this equation for speed, well, when it's stalled, the speed is 0. Set the speed to 0. Now you can solve this equation for torque, stall torque. So you have, again, these are the legend shows the colors. The blue is for the DC, and the orange here is for the PWM. And so you'll be able to compare those. So that's just an example. You have this, obviously, again, you got to put your own numbers in here. And then you can just have some tables and some plots ready to go here. So when all is said and done, you should have something that looks like this. So in other words, you'll have your plots for both DC power and using the PWM signal from the batteries for 9 volts, 4.5, 6.75, and then you can plot these other things that are being asked for, right? This is the no load speed versus DC voltage, and so on. So you can see, should get something that kind of looks like that. And again, don't forget to put in the trend lines on all these different plots here. Okay, so here's the different plots that you need to create, and then you need to answer the concept questions. Run this test on the motor. What are we expecting? Are we expecting that the you know, using a constant voltage with a DC voltage supply, is that going to look like, you know, at 4.5 volts constant voltage? Should that look like 50% duty cycle with a PWM? And then what about the equations? Should they be linear or not? Um, so anyways, you just need to put in your observations for these different plots. What are you expecting? Does torque depend on both voltage or current, or just current? So anyways, just let me know if you have any questions. Just one last thing. If you go to the Dropbox, you can see that there's a rubric. So again, it'd be good to go through the rubric, make sure that you have everything that you need in the rubric, you know, that you've addressed all these different items in the rubric. So hope you have fun with this lab.